Welcome back. In this session, we discuss about bitwise operators. The bitwise operators works on bits of the operands. That is, here the operation is performed bit by bit on the operands. Okay. So, the following are the bitwise operators: bitwise AND, bitwise OR, bitwise XOR or exclusive OR, bitwise complement. See, the last two are called shift operators and they perform on a single operand. Here also the operation is performed on the bits, so we can call them as special cases of bitwise operators. So, we have left shift operator and right shift operators. Now, let us consider the bitwise AND operator. My dear friend, the output of bitwise AND is 1 only when the corresponding bits of two operands is 1. That is, suppose consider the bit position of A, bit position of B, then what about the bit position of A and B? So, for bit position of A there are two possibilities, it can be either 0 or 1. Similarly, bit position of B can be either 0 or 1. So, the possibilities are 4 possibilities: 0 0, 0 1, 1 0, 1 1. So, the bit of A and B is 1 only when the bit position of A and B both are 1, otherwise it is 0. So, that is about bitwise AND table, okay, for a corresponding bit position of A and B, right. Now, look at this, here I am considering 8 bit numbers. See, my dear friends, it is the binary representation of number in or using 8 bits, right. Suppose if you want 16 bits, you can write 16 bits also. Here for easy understanding, I am considering 8 bit numbers. Now, this is a binary format of 12 and this is binary format of 25. I want bitwise AND operation between 25 and 12. So, let us consider. So, what we need to do, sir? We need to identify the corresponding bits. So, both are 0, so the resultant is 0. Both are 0, resultant is 0. Both bits are 0, resultant is 0. 0 1, still resultant is 0 only, because when both are 1, then only resultant is 1. Both are 1, here you get 1. 1 0 is 0, 0 0 0, 0 1 also 0. So, this is your 25 and 12. Now, you have to write it in decimal format. So, it is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So, the corresponding decimal number is, because all these are 0, only 2 cube into 1, 2 cube into 1, which is nothing but 8. So, 25 and 12, the bitwise AND operation between 25 and 12 is 8, my dear friends. So, this is how bitwise AND operation is performed. Now, what about bitwise OR operator? Consider bit of A, bit of B and bit position of A or B. So, possibilities 0 0, 0 1, 1 0, 1 1, and here when both are 0, then only bitwise OR is 0. In remaining all cases it is 1. It is 0 when both bits are 0. Bitwise OR is 0 only when both bits are 0. Okay? The output of bitwise OR is 0 when the corresponding bits of two operands is 0. So, now let us consider this 8 bit numbers and their bitwise OR operation. Now, let us see this: 0 0, corresponding bit is 0, 0 0 0, 0 0 0, 0 1, it is 1, 1 1 1, 1 0 1, 0 0 0, 0 1 1. Now, let us see what is the output. So, it is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. So, the corresponding decimal number is 2 power 4 plus 2 cube plus 2 square, and it is 2 power 0 means 1. So, it is 16 plus 8 plus 4 plus 1, which is nothing but 29. So, the bitwise OR operation between 12 and 25 is 29. You can try different numbers, my dear friends. Okay, you can convert a number into binary format and then we can perform the bitwise AND or OR operation accordingly. The next operator is bitwise XOR. The output of bitwise XOR is 1 only when the corresponding bits of the two operands are opposite. Means if one bit is 0, the other bit should be 1 or vice versa. Then only the corresponding bit of XOR is 1. So, it is like this: bit A, bit B, the XOR bit. The possible combination 0 0, 0 1, 1 0, 1 1. So, if the bits of the operands are opposite, that is 0 1 or 1 0, then only the bit of XOR is 1. In our case, it is 0. So, here if you consider 12 25 XOR you want, 0 0 is 0, 0 0 0, 0 0 0, 0 1 is 1, but 1 1 is 0 only, 1 0 is again 1, 0 0 0, 0 1 it is 1. So, here it is 2 power 0, 2 square, 2 cube, 2 power 4. So, the corresponding number is 2 power 4 16, 2 square is 4, 2 power 0 is 1, so that 21. So, this is about bitwise XOR. Let us consider the following program. We already verified this manually. Let us run this program and verify these outputs. So, the bitwise AND of 12 and 25 is 8, bitwise OR operation between 12 and 25 was 29 and bitwise exclusive OR of 12 and 25 is 21. Manually we verified. Let us run and verify the output. And you can see the output 8, 29 and 21. You can try different examples, my dear friends. The next operator is bitwise complement. It is an unary operator. So, what it will do, sir? It will just flip the bit. So, ones are converted to 0 and zeros are converted to ones. So, consider the following example 35. So, 35 is given here. What you do? Flip the bits. All zeros are converted to ones, 1 is converted to 0, zeros converted to ones, ones are converted to 0. So, this is your complement. So, actually the decimal equivalent is 220, but if you print it, you will not get 220, instead you get minus 36. Dear friends, whenever the leading bit is 1 after doing the complement, you are not actually printing the number, it is a signed representation. The answer in this case is 2's complement of this number. 2's complement of this number is answer. 2's complement of this is the answer. 2's complement means again converted to original number, add 1. So, whatever number you are going to get, put a minus sign for that, that is the answer. Actually, there are two methods here. Let me give you both the methods. Remember, my dear friends, only when the leading bit is 1, you have to use this particular method. If the leading bit is 0, directly the decimal representation is the answer. If leading bit is 1, 2's complement of this number is the answer. So, finding 2's complement of this number, there are two methods. 2's complement of this number we can find by two methods. First method is, let me explain here. See, you identify where you are getting zeros, okay. So, this is 2 power 0, this is 2 power 1, 2 square, 2 cube, 2 power 4 and it is 2 power 5. So, what we need to do is take negative values, that is minus 2 power 5, wherever you are getting zeros there only, corresponding powers of 2 you have to consider. The corresponding powers of 2 where you are getting zeros, 2 power 5 with a minus sign, 2 power 1 with a minus sign, 2 power 0 with a minus sign. After that you subtract with one more 1, minus 1, that is your answer. So, the simplified answer is minus 36. This is method 1. To get this answer or the signed, assuming it as a signed representation, the corresponding answer is minus 36. The second method is 2's complement of this number. See, actually all the numbers are flipped or all the bits are flipped, that is you get the original number again. So, directly you can start with the original number 0 0 1 0 0 0 1 1, then add 1. So, 1 plus 1 is, do not write 2 sir, it is a binary addition 1 0, 1 plus 1 1 0, this is 1, this is 0 0 1 0 0. So, this is your answer, minus of that is your answer. So, when you write the corresponding binary representation, so here it is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. So, it is 2 power 5 which is 32, 2 square which is 4. So, the answer is minus 36. Next example. So, again we got after complement you got leading one. So, we can use method 1 or method 2. So, you have to identify zeros. So, this correspond to 2 power 0, 2 power 1, this 2 square, 2 cube. So, the corresponding answer is minus 2 cube, minus 2 square, minus 1. So, that is minus 8, minus 4, minus 12, minus 1 which is minus 13. We can also use method 2. So, for that we have to use that 2's complement of this number. So, first all the bits are flipped. So, you get the original number only, that is 4 zeros 1 1 0 0, then add 1. So, it is 1 0 1 1 all zeros with a minus sign. So, write the corresponding decimal format, that is the answer. So, what is the answer here sir? Minus 30. Next one, see here it is a 8-bit number. See, the answer may be different for 8-bit and 16-bit, my dear friends, please note that. For this 16-bit number, the complement, if you observe, the leading bit is 0. So, directly decimal format of this is the answer. Directly write down the decimal format 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. So, what is the answer for complement of 220 sir? 2 power 5, that is 32 plus 2 plus 1. So, directly the answer is 35, no changing. If it is leading bit is 0, if leading bit is 1, okay, it is actually interpreted as signed representation of the number. Because of that, you have to do the method 1 or method 2 to get the exact answer for that value. Now, suppose if the same 220 is represented as a 16-bit number. So, for 220 this is the corresponding complement and you find leading one. So, we have to use method 1 or method 2. For method 1, this is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. We are interested in the positions of zeros. So, what is the answer, my dear friends? The answer for 220 complement is minus 2 power 7, minus 2 power 6, minus 2 power 4, minus 2 cube, minus 2 square, minus 1. It is 128, 64, then 16, 8, 4 and 1. 12, 13, 19, 19 plus 4 is 23, 31 and it is 10, 12, 221. So, you get minus 221 as the answer. You can also try the method 2. So, for method 2, what we need to do? We need to consider the original number. See, original number plus 1, only this bit position will change. So, let me write down how many zeros sir? 8 zeros. I am writing direct answer sir. 7, 8, then 1, 1, 0, 1, 1, 1, 0 and this will change to 1. And which for this we have to put a minus sign which is minus 221. So, this is how we get the answer, my dear friends. So, let us experiment with this. Let us write this program and try to check the output. Let us consider the following program. We already verified manually. Let us run the code and verify the output. In this program, I am using this fixed length integers. Okay. So, the fixed length integers are available in this particular library stdint.h. See, if I write int 8 underscore t, it represents 8-bit integer. Similarly, if I use int 16 underscore t, it represents 16-bit integer. You can also use 32-bit integer, 64, that is different bit integers you can represent using this fixed length integers, my dear friends. Because in our problem, as I done manually, for 8-bit integer and for 16-bit integer, especially for 220, the answer is different. So let us verify using this fixed length integers. So here I am using 8-bit integer. Let us save this and run the program and verify whether the outputs which we got are correct or not. So these are the outputs which we got. For 35 complement was minus 36, for 12 the complement is minus 13, but for 220 the complement is plus 35. So let us run the code and verify the output. And you can verify the outputs are minus 36, minus 13 and 35. Let us use 16-bit integers and verify the output. For 16-bit integers, complement of 35 is minus 36, no change. Complement of 12 is also minus 13, but complement of 220 is minus 221. So let us verify the output. You can clearly see the output. Here complement of 220 for 16-bit integer is minus 221. Okay. So this is about bitwise complement, my dear friends. Consider the following problem. It was asked in GATE. So here character A, B, C, D, E are defined. For A, we are assigning character capital P. For your information, ASCII value of capital P is 80. And for B, we are assigning small x, whose ASCII value is 120. And for C, some expression is assigned. Similarly, for D and E also expression is assigned. So we need to find the value and assign the particular value to C, D, E respectively. Then we need to print the character. So we need to identify what are those characters. See, for helping you, he already given the ASCII values from capital A to capital Z. Of course, all the ASCII values are not given, but you can easily identify. For example, C is given means D is 68. Actually, P is the 16th character. From A is first, P is 16th, whose ASCII value would be 80. Like that, you can easily identify. Am I clear? And when you know small z, you know small y is 121, small x is 120. Like that, you can find the ASCII value of 120 also. Even for star, plus and minus also ASCII values are given, which were used in these expressions. Okay. So we need to simplify and get the values of CDE, first ASCII values, then we need to identify the corresponding characters. Now if you observe, I just written A, which is capital P 80. So that is the binary format of 80, and this is the binary format of small x, which is 120. Now when I want A and B, what is A and B, my dear friends? A and B means if both bits are 1, then only you get 1, otherwise it is 0. So it is 1 here, it is 0 here, it is 1 here, it is 0, 0, 0, 0. So it is exactly same as A only, so which is 80. Now A or B, if you consider, this is 0, this is 1, this is 1, 1, 1, 0, 0, 0, which is exactly same as B, which is 120. Now what about exclusive OR? 0, 0, 1, 1 is also 0, 0, 1 is 1, 1, 1 is 0, 0, 1 is 1, 0, 0, 0. Actually, if you want, you can simplify and verify what is this answer. It is 2 power 0, 2 power 1, 2 power 2, 2 cube, 2 power 4, 2 power 5, 32 plus 8, which is 40. So the ASCII value for this fellow is 40. So here if you observe, C is bitwise operation between A and B, which is nothing but 80, plus ASCII value of star, which is 42, which is 122, which is small z. Now what about this A or B is 120 minus ASCII value of minus is 45, which is nothing but 75. So 75 is, I think, K. In just because I just remember the value, you can just find out, sir, because you can start from A, B, C, D, like that you can identify. Okay, it should be capital K. Then A exclusive or B, which is 40, plus ASCII value of plus, which is 43, which is 83, and it is capital S. So, if you print the characters, you are going to get small z, capital K and capital S. So, that is the output for this particular program, sir, which is option A. Am I clear? So, because you are printing the characters, not the values. So, if you print the values, you will get this. Suppose if you do %LD, you would have got the option B, my dear friends. Okay? Let us run this code. Let us see the output. Save the program and run. And you can see the output is Z, K, S. The next operators are shift operators. So, we have right shift and left shift operators. See, these operators move bits to the right or left by specified number of bits. And the operands for these operators may be any integer type, even you can have character also. But shift operators on unsigned numbers are implementation independent. So, on every machine they perform in the same manner. So, for portability purpose, it is best to perform shift operators on unsigned numbers. So, we are going to perform only on unsigned numbers only. The right shift operator. See, right shift operator shift all bits towards right by a specified number of bits. So, for example, if I write A right shift I, what is the result, sir? When the bits in A are shifted right by I places. That is, the bits in A are shifted right by I places. But when you shift the bits right by I places, the rightmost I bits are removed. To compensate that, on the left side, we are going to add I zeros, leading I zeros we are going to add. That is how the right shift will be performed. For example, consider 12, it is 4 zeros followed by 1 1 0 0. When you do right shift, the right shift suppose by 2 bits, the rightmost 2 bits are removed. So, on the left we are going to add 2 leading zeros. How many bits you are going to move to the right, that many leading zeros you are going to add. So, the answer is 3. My dear friends, you can get this answer by dividing this 12 by 2 power. How many bits you moved right? 2 na? 2 power 2, that is 12 by 4, which is 3. Now, left shift. Left shift operator shift all bits towards left by a specified number of bits. So, the value of A left shift I is the result when the bits in A are shifted left by I places. That is, the bits are moved or shifted left by I places. That means, leftmost I bits are removed. To compensate that, we are going to add trailing zeros. How many? How many bits you shifted left, that many zeros you are going to add on the right. Same story, 12 we are having 4 zeros 1 1 0 0. You left shift by 2 bits. So, leftmost 2 bits are removed. We are going to add trailing zeros. Towards the end, we are going to add 2 zeros, and this is the answer, which is 48. Actually, you can obtain like this: 12 multiplied with 2 power. How many bits you shifted left? 2 na? 2 square. 12 into 4, which is 48. So, the right shift of x by I bits can be obtained by dividing x with 2 power I. Similarly, the left shift of x by I bits can be obtained by multiplying x with 2 power I. Okay. So, let us see example. So, this is 64 in binary format. I am assuming it is a 8-bit number. Now, right shift by 1 bit, we can obtain it by dividing 64 by 2. So, the answer should be 32. You can verify this. This is 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, and this is 2 power 5, which is nothing but 32. And right shift by 2 bits, 64 by 2 square, which is nothing but 64 by 4 means 16. You can verify this. Okay. This is 2 power 0, 2 power 1, 2 square, 2 cube, and it is 2 power 4, which is nothing but 16. And right shift right shift by 3 bits, 64 by 2 cube, that is 64 by 8, which is nothing but 8. Now let us consider the left shift, 16 binary format assuming 8 bit number, 16 left shift by 1 bit. You can obtain it by multiplying 16 with 2. 16 into 2 is 32. Left shift by 2 bits, 16 into 2 square, which is nothing but 16 into 4, yani 64. And left shift by 3 bits, 16 into 2 cube, which is nothing but 16 into 8, yani 128. Let us see this with a program. Now in this program, we define an integer variable a. For that we are assigning the value 64. So we are doing a right shift by 1 bit position, 2 bit positions and 3 bit positions. Okay. Similarly, left shift 1 bit, 2 bit and 3 bit positions. So here it should be 64 by 2, that is 32, 64 by 4, that is 16, and 64 by 2 cube, which is nothing but 8. So when you do left shift, you have to multiply with 2, okay, 2 power I, where I is number of bits you are shifting to the left. So 64 into 2, which is 128. Next one 64 into 2 square, which is nothing but 256. And next one 64 into 2 cube, 64 into 8, which is nothing but 5 and 2. So these are the expected outputs, my dear friends. Let us run and verify the output. And you can see 32, 16, 8 and 128, 156 and 5 and 2. The precedence of bitwise operators. See, actually shift operators are having higher precedence than the bitwise binary operator, that is bitwise AND, bitwise OR and bitwise XOR. But within bitwise AND, OR, XOR and OR, bitwise AND is having higher precedence than bitwise XOR, then finally bitwise OR. So this is about the precedence of bitwise operators, and both are left to right associative, my dear friends. So in the next topic, we will try to see the complete precedence of operators, and we also try to see one very good mnemonic to remember the precedence of all the operators. And this is about your bitwise operators, my dear friends. Thank you.